I'm Josef, one of the organizers, but I have been doing it for more than 25 years now. Yeah, that's a good idea. With some combinations of machine learning for theorem proving, and as you just heard, it seems to be an exciting topic these days, even though for me it was exciting topic 25 years ago. And I would say there are three motivations that I'm somehow distinguishing into what we are doing. And like most of you here are probably the motivation, like, let's formalize mathematics, let's do math on computers, let's do, I would call it the QED dream. So I don't know how much you and any of you know about it, but some more than 20 years ago, there was this QED manifesto and QED workshop where people basically wrote up this proclamation. Why would it be good to formalize math for all sorts of reasons? And I would say, if you read it, I very much recommend reading it. I think Frank might have it cached somewhere on his web pages, being the guardian of the history of the two QED workshops. By the way, we did a QED workshop after 20 years, 10 years ago, right? So it will be like 30 years now. I very much invite you to read it because you know, for some people it feels new when they hear all these ideas from, I don't know, from some YouTubes of Kevin or whatever, but these are really old ideas. So that's like one dream. I would say there are two related dreams to it, and one of the related dreams is the dream of omnipotent automated reasoning, automated theorem proving crazy hard mathematical theorems, open conjectures, etc. And that's a dream which is, I would say, equally old. Like you could even say that the field of automated theorem proving is one of the oldest fields of artificial intelligence. Like some of the logic theories by Simon and Newell is today often cited as the first AI system ever, which may be slightly questionable, but it's definitely an example of a very old AI system. And the field of automated theorem proving in the beginnings of AI especially was really like people like John McCarthy were very much into this stream of AI where you would translate sort of hard problems, not just mathematical but scientific, into, you would sort of reduce them into mathematics, and you would reduce mathematics into logic, which is like this thing which happened with this sort of Leibniz, Hilbert's, Russell program at the beginning of the 20th century. And then you would solve your problems by search, right? Like by proof search. You would, in a similar way as you find the proof of Fermat's last theorem automatically, you would solve all sorts of other problems, I don't know, from physics or whatever, by a reduction to mathematics and to logic. And that's sort of the third dream. Like the third dream is the field, the dream of basically AI solving all sorts of, let's say, scientific problems. And obviously that dream is slightly fuzzier, and it's so obviously that everybody today cries, I don't know, deep learning, or not even deep learning anymore. Everybody is shouting large language models, right? Or whatever. But like the dream of reducing all sorts of scientific and maybe other problems, like for example, John McCarthy has a nice paper from, I don't know, beginning of 1990s, I think, or maybe end of 1990s, about reducing legal and political proposals to some pseudo-proof, to some sort of pseudo-logic. And he actually motivates it by the progress in formal mathematics and automated theorem proving. So these are sort of the three dreams which are somehow out there, and they are connected in various ways, right? Like if we manage to put all of the math, very advanced math, into some deeply computer understandable form, not just archive, then we can, for example, train combinations of various machine learning and research systems on that, which is, like I said, what I have been doing for more than 20 years. So that's just to sort of brainwash you a bit with, well, don't just focus on formalization of math, like be aware of the fact that this may be a part of something equally or even more crazy and interesting if this sort of QED dream progresses. And well, like you might have seen this book, like the Logic Comics. If not, then definitely get it and read it. Where there is this nice picture about obviously the hero of the book is Russell telling his life story, and here on the slide he's saying how basically he got inspired by Leibniz, the guy who is often quoted for this calculimus, the idea let us calculate, where basically he envisions that sometime in the future we will be able to reduce a lot of our scientific or even societal issues and problems just to reasoning, just to formal calculation, like things like that, right? So that's actually what might be sort of happening today if the sort of AI and automated reasoning and formalization programs proceed reasonably, right? Like you could. We were discussing yesterday, for example, formalization of law, right? Like we could really today have a shot at embedding a lot of law, which is fuzzy and natural language based, into logic in the same way as we are trying to embed mathematics into, I don't know, lean or whatever. Okay, so now I burned like 10 minutes of my talk, so now you see that the slides will definitely not reach its end. And like this is just like one way how we could sort of do this process of, like, let's say, at least automating math, right? Like, so we know that well, we don't know exactly what it is that mathematicians are doing. Well, maybe some of you know, because some of you are pretty good mathematicians here. But like the fuzzy idea is that we have a lot of these pattern matching, analogizing, learning, inducing knowledge from examples, capabilities. And then mathematicians also are pretty good at deductive reasoning, at knowing how to compose pieces of knowledge into proofs and into things that we can really proof check today. And sometimes these things are very surprising, like they can be surprising both positively and negatively. They can really bring you new knowledge. And there seem to be some feedback loops between these two processes. So if you are not succeeding in composing new proofs, maybe you will learn from your failures, and maybe your next attempt will be better. And obviously we do this knowing a lot of stuff, like they have beaten into a lot of textbooks of math, etc. So if we want to somehow start doing this on computers, then there is one good resource that we could sort of use for training these sort of automated mathematicians, or starting the research and training these automated mathematicians. And that's exactly these large libraries of formal proofs that have really been existing for decades today. I would say I started like 25 years ago with the Mizar Mathematical Library, which already like in 2000 had like 700 mathematical articles in it about all sorts of mathematical areas. And like you could really try to take such a big formal corpus today. I don't know, Isabel, Clean would be the biggest ones, and try to do or develop some strong automated theorem proving and machine learning capabilities. So the rest of the story is basically some sort of attempts in this direction, like mostly talking about our work, like the work that me and my team have been doing. And just one funny picture from this Logicomics book. Like, when I started to do this, and not just me, other people, like today, AI in the minds of many people is machine learning and blah, blah, blah. I would say the two communities, the sort of formal reasoning, the sort of precise logic community, and the machine learning community don't get together too well. Like there is sort of a lot of resistance from both sides. Like today the situation is much better, but there is sort of suspicion which can be slightly traced back to a famous debate between these two giants of mathematics, which is this picture from Logicomics, where there is the sort of Hilbert, Russell, and Frege, etc. program, which really brought us the symbolic logic, the formalization. You could even say computers, like computers are basically symbolic logic machines. And then there is the sort of intuition-based approach, which sort of Poincaré would be a sort of an example here, which obviously doesn't mean that he couldn't do proofs, but like the fear that the formality is sort of taking us in the wrong direction, right? And these two views you can encounter quite often still today when you are trying to combine some precise formal reasoning with some sort of imprecise statistical machine learning, for example, or even some sort of inductive pattern matching, etc. So I would say it's not a bug, it's probably a feature. Like the humans have somehow all these capabilities and they somehow combine them. The sort of learning and induction from examples is a very important capability. The sort of capability to manipulate symbol and do deductions is also an extremely, like I said, we wouldn't be able to program computers, right? Like if we didn't have that. But I would say the field is very interesting just because of this, or it's one of the big reasons why the field is quite interesting, because it sort of forces the two camps in AI to somehow come to terms. You cannot do theorems just by machine learning, or you cannot like learn just by theorem. I'll skip Poincaré. Like an interesting guy in this history is Turing, who probably faced some of these issues himself, while like being basically the guy who brought us computers, or not one of the guys who brought us computers, and who is particularly famous for the halting problem and the undecidability of, first of all, logic together with church. And you could sort of see him as going through some sort of change during the Second World War when he was working on basically enigma, right? Like hacking the coding systems of this country, and like he can really be seen as not only the guy who brought us computers, but also the guy who very much brought us artificial intelligence in his 1950 paper, Computing Machinery and Intelligence, where he sort of debates like why machines wouldn't be able to think, and introduces the Turing test. And for example, he has these goals, right? What would be the best fields? So this is the last section called Learning Machines of this 1950 foundational paper on AI, where he says like what would be the best fields to start training these learning machines on. And he for example, proposes to start training systems that would be playing chess or some other games, which, by the way, like each of you have seen, this AlphaGo and AlphaZero became really very real recently. And the question is, why would we limit ourselves to chess or some boring limited games? Why wouldn't we do this with math, which is basically a game? Right? When you do it on a computer in your Lean or Isabelle or Coq or Mizar or Hall, it is a game. Like Craig always says that this is a game for me, right? Like it's sort of an addictive game for some of us, I would say. I'm looking at Mario here. So can we really train a superhuman game for math? Like let's say we can train it today for Go. So that's sort of a research question. I would say currently we cannot, like you shouldn't sort of trust the headlines, which for some 6-7 years have now been announcing breakthrough in machines overtaking humans in mathematics about every summer during some crazy summer quanta or nature season. So no, currently. There are sort of isolated areas, like for example, equational algebra, where machines or automated theorem provers have been very good for, let's say, 3-4 decades by now, where people can prove open conjectures that sort of mathematicians cannot. But I would say in the general hard, Fermat's last theorem style mathematics, the technology certainly isn't on a human level today. I'll skip some of this motivation because I talked about it. You probably know, and you have heard it yesterday, that this is both some sort of blue sky AI, which is today really bombarding you from all sorts of newspaper titles. But one reason how I was getting funded before this AI hype wave came was that these systems that we are building, for example, hammers or the tactical systems, can really assist people like you, people who do want to formalize mathematics. And there is this bunch of projects like formal proof of the Kepler conjecture, the Phi-Thomson theorem, etc., concert, where if we make it work in like Isabelle and Sledgehammer is one of the biggest success of proof automation, then we really managed to speed up the formalization verification in these systems. So this is probably the slide where I will spend most of my time. Control the time. So what do we do today? What we have been doing for these last years can be divided into a couple of branches. Well, like you could say that one way how to divide it is basically on which level you combine the machine learning with the, let's say, theorem proving or some other automated reasoning technology. And what I have here are some sort of examples of high-level guidance, low-level guidance, mid-level guidance, and some other topics, like for example, I don't know, theory exploration, feedback between the learning and proving, and auto-formalization, which is like taking some natural language or LaTeX text on some paper and trying to make it automatically parse in your favorite proof assistant. And I would say the high-level thing is probably the earliest and easiest, and also it was the most pressing one when we, let's say 20 years ago, when somebody like me or Larry Paulson started to take these big corpora of, I don't know, Isabel or Mizar, and we really wanted to prove a new conjecture on top of them. I know Mizar could have at the time something like 30,000 lemmas in it, and you simply couldn't feed 30,000 lemmas to automated theorem provers at the time. They weren't constructed. They were typically working with like 4 to 20 axioms. So what you had to come up with was some method that would, from this big knowledge, this big collection of textbooks that exists in some formal form, extract the most relevant conjectures for your premises for your new conjecture. And that became a pretty well-established topic in machine learning for theorem proving called premise selection, where you basically construct the machine learning task by saying, well, hey, I already have like 30,000 previous proofs in my library, so I can do some training, some machine learning on them, because each of them has a conjecture and each of them has some space of available premises from which only a few were actually useful. So whatever is my favorite machine learning method, I can try to train it on that. And when I see a new conjecture, I can try to run it and see how much it helps me to prove the next conjecture. So these premise selectors are today pretty standard parts of, for example, the sledgehammer system in Isabel, where it's running a very fast machine learning methods like naive Bayes or Immediate Snyder. Maybe I'll sort of skip the other high-level tasks and give you just examples of the low-level stuff. So the low-level stuff is sort of the opposite of the high-level stuff, in the sense that you can take these automated theorem provers, which are really, like you probably didn't hear a talk about those yet, but in some sense, the field of automated reasoning is split into, you could say, interactive theorem proving and automated theorem proving. So in interactive theorem proving, you really do it manually and you hope that the system people will provide you with suitable automation. In automated theorem proving, you sort of hope you are constructing systems which are really trying to do it all for you. And obviously, it very often fails. So these are highly efficient symbolic systems which take some conjecture and axioms, and they use some calculus, like for example, the tableau calculus, the superposition, resolution calculus, and we know typically that they are complete. So we know that if you give them infinite amount of time, they will give you a proof, provided there is a proof. But it's typically they encounter some sort of combinatorial explosion, because like this is obviously hard, right? Like the task is semi-decidable. So the sort of ambitious thing with this sort of low-level guidance you can do is to, instead of using whatever are some pre-programmed heuristic for guiding these automated theorem provers, like typically like the very high-level picture of how these systems work, for example, in the superposition and resolution calculus, is that I give you axioms and a conjecture, I negate the conjecture, And now from the axioms and the negated conjecture, I'm trying to derive a contradiction. And the way I'm doing it is that I qualify everything. I put it into first order clauses. And now I'm, for example, using the resolution and rewriting rules to get to contradiction, which is the empty clause. The empty clause is a disjunction of 0 literals. And the heuristic could be that you prefer the clauses which have like fewer literals in them, because that sort of gets you to the empty clause, which has 0 literals. But obviously it's just a heuristic because the problem is very hard, semi-decidable. So sometimes you really need to generate very big clauses. So the way how you would like to plug in machine learning into it is that maybe you have a big collection of problems that you have solved already. Like, for example, you can extract them from these big ATP libraries. Maybe you can run the automated theorem provers, at least on some of them, and prove them. And then when you unleash this automated theorem prover on a new problem, it will sort of be guided by some trained machine learner in saying what it should do, like which of these inferences it should prefer in particular situations, when sort of running into situations that sort of look like some previous situations that it already encountered. It might not do too much sort of blind search in those situations and instead go sort of in the direction that actually turned out to be good. So this is ambitious because, for example, if you throw, I don't know, deep neural networks or large language models into it, then this something like ChatGPT will probably do like 1 inference per second, which is horribly slow, right? Like the ATPs are very fast symbolic engines that can do 100,000 inference per second. So if you are perfectly correct, then fine. If the proof takes 100 steps, then it will take you 100 seconds. But like that typically doesn't happen, right? Like, because this is a new problem, hard problem, you need to do some search and some backtracking. So for this sort of low-level guidance of these highly efficient automated theorem provers, you typically need to very carefully choose your trade-offs between the speed and the performance of the machine learning methods with which you are guiding this. And sometimes this leads to like multi-layered architectures. For example, you may have some very fast learning architectures at the top and some slowish architectures to do the sort of last step reasoning. Because this is so hard, people have successfully developed something in between these two approaches. So the premise selection is sort of easy from this point of view, because you call the machine learner only once when it tells you what to select from this large mathematical library, and then you just give it to the automated theorem prover, to the hammer, and it sort of goes with it, right? Like you can call it with, I don't know, 10 different suggestions, and then you call the automated theorem prover 10 times, but it's still very few calls to the machine learner, which can be expensive, it can be some crazy large neural network. And if you spend 1 second on that, that's fine, because then the automated theorem prover runs, I don't know, for 10 seconds. So the mid-level guidance is some sort of approach in trying to sort of get the best of the two worlds. And I would say the biggest example of this mid-level approach is today basically machine learning based guidance of interactive theorem provers like Lean, Koch, Isabelle, etc. whole where the machine learner is called to recommend the tactical steps that you are doing in these interactive theorem provers, especially the tactical ones, like in the sort of declarative ones that is sort of more complicated. But if you look at something like, for example, Koch or Hall or Lean, it's relatively easy to train something, and already very simple methods like k-nearest neighbor work extremely well on this, on a large repository of proofs, where basically it looks at the proof state, the current proof state, and it tells you, well, now use induct, or whatever, now use rewrite, or now use the Mason tactic, or whatever, grind in PBS, right? So this means that the machine learner doesn't need to be so fast as in the low-level guidance, because you don't do these technical steps so often as the sort of low-level steps in the automated theorem theories. You can spend reasonable time on that. And then what you have to do, and what is actually quite technically challenging in reasonably advanced interactive theorem theories, is to combine it with some sort of proof search in these technical theorem theories, which is really non-trivial engineering work. So I would say today that there is a lot of experiments like with this technology in interactive theorem theories, but there is only like very few systems that actually work and that the users can experiment with, because like the engineering work is really non-trivial to sort of make it useful. For example, make it learn from the formalization that the user is doing. So as the user is introducing new concepts and new lemmas, etc., you need to do something, right? Like if you only train language model on everything that is already in the library, well, what do you do when the user introduces 10 new concepts? Like, will you retrain a large language model for 1 year, or like you cannot, right? Like so there is sort of a lot of these engineering issues, but I would say this is like a very rewarding field to explore. Okay, so this was a bit of the overview, and I can probably go into some of the demos. Well, maybe before I go there, I don't know how much from probably Peter Kepka's talk and Manuel Eberl's talk, you may have seen that there are these things called hammers, like sledgehammer in Isabelle, and the whole macro system today is one big hammer, right? Like you only call automated theorem theories steered by some sort of premise selection. So this is really in the Isabelle system like a very powerful and used method for assisting the users, and it has been done in all sorts of other systems, but it's by far most used in Isabelle. And the idea is sort of what I already explained to some extent. So you have a proof assistant, which in this case maybe Isabelle Hall, something running in high-order logic, big libraries, etc. And then you do have some current goal that you want to prove in the system, formulated in this sort of more rich logic. Then what the hammer does is that it takes your goal and the whole theories that you have available, and it does two things. It selects or proposes by all sorts of methods, some of them being machine learning, the most relevant premises for this current goal that you have. And then it translates from the sort of richer logic which you are in, like in, for example, in Cockhammer. This is really non-trivial because you need to translate from type theory to first-order logic. So that's even in Isabelle, which is sort of simply type of polymorphic high-order logic, there are really many possible options how to do the translation from the high-order logic to first-order logic. And once you have done it, you ship it over to these powerful first-order automated theorem provers like eProver or Vampire in this case, and you hope for the best. You hope that these things will give you a proof. If that happens, you try to reconstruct the ATP proof into an ITP proof, which will go through the kernel of this secure formal proof assistant like Isabel. So sometimes what can happen is that there is a bug in the automated theorem prover, which are sort of less strict about the security. Or what can happen is that some of these translations are unsound because they are sort of trying to simplify things so that they give better chances to the automated theorem provers. But the price is that sometimes the automated theorem provers can sort of abuse the simplification and find a proof which is actually not a proof in the origins. But anyway, well, like these methods have been developed quite a bit. And some 10 years ago, they could do like 40 to 45% on these various systems, libraries, and quite recently we did about 60% on the Mizar library by basically putting all sorts of machine learning methods into these low-level systems, but also by developing a lot of useful machine learning methods for the task of premise selection. So that's just for you to know that in some of these systems, in particular Isabel, and in particular an approach, if you play with them and call a hammer or a sledgehammer, some of these things are happening sort of behind the scenes, and they sort of might be happening to you also in some other theorem provers. Like I think there is a push in lean to integrate automated theorem provers into it, etc. Maybe I'll now show you at least one demo of how the tactical guidance works, but I'm not sure if this is visible. It's probably not too visible, right? Oh, well, I'll try to run it anyway.
Full screen will help.
Sorry?
Full screen will help.
So, yeah. It's me. Yeah, this is a video. So this is the tactical learning guided tactical theory. I employed the first system which really made it fully usable and also made it quite strong, which is called Tactical by Thibaut Gauthier. So what he is doing here is saying, I want to TTT this particular goal, then the TTT is loading a lot of previous tactics and theorems, and then what it's doing when it sort of spits out these ASM syntec and is that it's basically doing some sort of Monte Carlo tree search guided by the knowledge learned from these previous 3,000 theorems and proofs, basically. So after occasionally it actually finds the proof and then it sort of spits it out. So this is sort of the mode of interaction that you get. Is this now you see that it's thinking really hard. So now again it tried to prove some theorem about mapping something on a list. And again, like after doing the sort of proof search guided by the trained machine learner, it finished the proof. So this is today. I think such systems exist in Coq and maybe Lean. I don't know what's the situation in Lean and whole light. And they are sort of more experimental than the hammer systems, but like for these complicated technical systems, this is like a very useful thing to have. And some of you might consider working on them. Like it's non-trivial, but it's like a so for example, this tactic-toe system can prove again something like 60 to 70% of the whole Flora library. So I guess I will stop here, and I guess if you want to hear about some of these other things you see on slide 11, then you can ask me, or I can give another talk.